Actually, I gave some exercises that we didn't correct yet. Maybe we can go through them and we can continue on what we said at the end of the lecture yesterday. So, you said you had a correction of something? You said you had done something? There is something on the board?
Both entropy,
Good.
But in dimension 1.
Dimension 1, yeah. Okay. You can come at the blackboard and quickly solve this, and then we will see how to...
Okay. So, I don't know. We wrote the lemma about the sequence that is non-negative and does that.
Maybe you can first, so are you proving this lemma or are you using it for the definition?
Yeah, no, to use it is simple for...
Maybe you can start by this simple thing. So how are you going to use it? And
we have a definition of entropy with...
This way you recall also the definition for those who don't remember or have not been here.
Yes, and okay, we have the sequence that is non-negative, and we should prove that this is like this.
Because this definition, yes, we should prove that this definition makes sense. So, can you recall the definition of ln of L for those who were not here at the beginning of the course?
It's just the number of words with length n.
The number of words?
Allowed words with length n.
In X.
In X, yes. So, the number of it's just because if we have all allowed words with length n and with length m, so we have all words, we have some different words with length n plus m, but maybe it's not all the words, so it's not the equality, but
maybe you can write this as a function from ln plus m of x yes.
And it's f from the word
exactly.
If this word is a lot, is a mix, so this word is missing, this word is
Yes.
So,
and what is an important
and this
feature of this function?
Injective, so we have this sign.
It's trivially injective because
but it can not be surjective, so we don't have this one. Maybe.
It can be non-surjective.
Non-surjective.
Or it need not be surjective. But if you say it cannot be surjective, it means something else. No, it's not. It's not.
So we're missing both then. definition of tangent. Yes. Section.
Yeah.
And beyond
Yeah.
the
So we have this one, and when we put the algorithm for this, we have like the sum. Yes.
Okay. So if we assume this lemma, then the entropy, maybe we can define in general the entropy as an infimum, because the infimum of a sequence always exists, and the entropy is equal to the limit, because that is direct from the lemma. It's direct from the lemma and the injectivity of this.
Yeah.
Okay. And now you want to prove the lemma?
Yes. Okay. First of all, the existence of infimum from the sequence is not negative, so it's bounded. So it has some infimum. And okay, first of all, let us Vn be divided by n. So we should prove that we have we should prove this one. Okay. First of all, we should know that, for example, we and k is now more than the because it's the sum of if n is natural.
So we assume this and we prove inductively on K thanks to this. Yes?
Okay. Then how to prove it? No, can I just put something away? Okay, so we have somewhere. Okay, what about the EMG? Plus M is no more than Vn. Ну, это значит то, что Vn плюс M, она лежит на отрезке от Vn до Vn, мы их делим там в каком-то отношении. Вот. Вот. Ну, значит, во-первых, это можно написать. Вот. Еще у нас есть такое соотношение, да? Значит, у нас есть две инфимум. Да? Вот, двоевое, да? То что значит это инфимум? Значит, что для любого эпсилона свойство наследственности найдется какой-то член последовательности. Вот, какой-то блокатор, ВНТ. Вот, но если там есть ВНТ, то это значит, что там есть все ВКНТ, причем они там будут, ну, понятно, что они больше инфимума, больше грамм инфимума, но при этом нет. Okay. So, if we have
you can speak Russian.
reason view, so for every epsilon we have m in neighborhood. We have neighborhood somewhere m, but it means that for all k we have that here too, because it lies on this interval. Okay, so the whole sequence of this one is here.
So, but by the way, so I think this is U and K, which is less than K UN. V and K, you have to divide V and K over K is less than Vn. No. V and K.
And K is n plus n three times.
Mm-hmm.
So, using that one, it means that it's no more than Vk plus Vk plus Vk, and Vn plus Vn plus Vn k
No,
times.
this is U.
Okay, but okay, we have U and K no more than U K.
K-U-N.
U-N.
Okay, and then you divide
By
NK.
So we have
No. Yes.
Yes. Okay.
NK is less than
Yeah. I'm sorry.
But that's what you were saying here.
Yeah. Okay. So the whole sequence is here of Venga. So what about another one? So what if we have some n that is more than n, but maybe it's not like nk. So we can divide with remainder, and we will see something like this. N is less than n. So it means that n is more than 4. We just rewrite it with the instead of u.
That you wrote U. Is U or
Yeah.
Okay.
Okay, and we can just say that V is no more than V1 because of that. We should just put n equal to 1, and V1 is the most of all, so we can just write that it's no more than V1. Okay, so what does it mean? It means that we have Vn, and V1 somewhere, and Vn is no more than the point that divides this interval with the relation equal to f. But r is less than n, so it's more than 1. Okay?
I don't understand this line.
Okay, it doesn't matter. So, okay, it means that we have something, we have this point that divides like okay, yeah.
Maybe you can write
like
Q over N.
But we can.
What is this notation, sorry? R, 2 points?
It means that the relation is like this. Okay, for example, it means that this point divides this interval like 1. So,
Relation is certain.
yeah, just,
Okay.
it means that this interval divided,
A to B.
Okay.
it means that it could be like 1 to 2. That is.
Okay.
So if this one to this one is like
Okay.
in Q, so we can make, okay, so now we can make R very small in comparison with NQ.
Mhm.
So this, all these points will be in some delta neighborhood. So if we choose first delta and then we can choose the epsilon, so later it will be in epsilon 2. Okay, like this.
Okay, but so okay, I understand what you mean, and another way of saying this is that here you have V and Q. You said that this is less than VQ or Vn. Your Vn is the one that is in the neighborhood. Okay. So this is less than Vn, and NQ over L is less than 1. NQ over L is less than 1. So you have Vn plus something which goes to
Yeah, we could just invert here.
which is less than epsilon.
And what is there? 1 plus 2 divided this one.
Oh, and Q is less than, it's even 0. Ah, yes, no, you cannot say this directly, I think. You
We
have this.
V1. Okay.
No, it's not multiplied by okay, yes, we can write V1 here if you want.
Yes.
V1. And V1 over L is for L big, it's less than epsilon.
Yeah.
I don't understand this. You cannot multiply this two, I think. The anytime
See,
job.
that's what is written here.
No.
No. Yeah. Okay.
But
Okay.
But I think it corresponds to what you said.
Yeah.
Okay.
So we know that the sequence.
I think it's proven.
Yeah.
So are you convinced, everyone? It's finished because then there exists a big N such that you are epsilon close to something which was epsilon close to the infimum. So you are kind of 2 epsilon close to the infimum. For every epsilon, you can find such a big N which is 2 epsilon close to the infimum, which means that the limit is the infimum. And what happens in higher dimension? Someone has thought about this? Or any questions on this proof? Something is not understood? So in higher dimension, we will not do it very fun. We will not do it in detail, but it's just that there is you have to understand what it means to be subadditive, and so how can you do the same kind of argument with the language? So in dimension 2, for example, the entropy can be taken as the limit of the exponential growth of the patterns over squares that are bigger and bigger. Okay? And what kind of subadditivity you have in dimension 1 we said that if we have a big pattern, then it's composed of two patterns, one of size m and one of size n. Maybe not all such pairs of patterns give an allowed pattern, but at least all allowed patterns give two allowed patterns like this. And in dimension 2, what is true?
Maybe you can split this big square into like one smaller square in like upper corner and one to another in like left lower corner and give some.
Right. Actually, what you say is, I think, is maybe one way also to formalize it is to say that in every dimension I could cut it into rectangles. So if I take U and M to be the set of allowed patterns over rectangle 0n and 0n. Okay, so in dimension 1 we had exactly this. This UN was set of allowed patterns with interval n. Maybe I should put one. Okay, so now I need two indexes, and I have UN n plus n prime, which is equal to UN n less than or equal to UN plus UN n prime, and the same on the other dimension. And a two-dimensional lemma would say that if we have this, then UN, maybe we can say UNM, or you can say UNN, don't care, over n times n, and n goes to infinity, converges to the infinity. Do you agree that with such a lemma we get to the similar, I mean, we get directly to the fact that the entropy also has a correct definition as a limit in dimension 2? Okay, I take this as a yes. Now, do you agree that you can trivially generalize this to every dimension by having many indices? So I will not write it. And actually, you can generalize it to groups, to some groups which are amenable, which means exactly that you can. I don't give the definition now, but amenability is a property of groups that Z to the D have, which means that you can cut things like this and things don't get too complicated. You can cut them and you can cover a big square with two rectangles such that the number of rectangles you need to cover compared to the size doesn't grow too fast. Anyway, I don't want to talk about this, it's just for you to know. But at least, yes, you can see that there is a trivial generalization to every dimension. And finally, you agree, maybe you don't, but I'm telling you that the proof is not more complicated than this. It's actually once you have the statement of the lemma, you know how to do it in Z, and you know how to do it in Z. So, we won't do it now. If you don't agree that it can be done, you can do it as well. Any questions on Fekete lemma and basic definition of topological entropy? Okay. So is there an exercise that you want to correct? That I gave, or that you want me to correct, or a question on what we've done so far? So let me give you an exercise. X is a letter T. Y is conjugate to X. What can you say on Y? I don't know if you realize that I like this kind of question. It's more about what, if I write this, what can I ever expect you to be able to say on Y? Even if you don't know the proof, but so I assume only this. I don't assume anything on entropy. So can you say something about the entropy, by the way?
It's equal.
It's equal, yes, to show this. So the entropy of Y is equal to entropy of X. So the entropy is the conjugacy invariant. Now, I'm not talking about entropy, I'm saying that X is an SFT. Maybe we want to know something on Y. Okay, can you show this? I give you some minutes, I think. So you take draft paper and you take back your definition of conjugacy and your definition of SFT, subshift of finite type. So the definition of conjugacy is a continuous reversible sheet invariant map, but you remember that we also have a characterization which is maybe more practical to use in this kind of proof.
Could you write
to be agreed.
Okay, from now. But this is not interesting for you because we've seen this in class. You all know perfectly what I've just written. And you know what I will write in 1 second? What I will write here? The characterization of conjugacy. I don't know, when you talk like this, I don't know if you want to say something or... This is written here, the definition, and there is a characterization in terms of, in the case of subshifts.
That can be defined by a local map, which takes at least maybe some number u small. Or maybe have to call this number.
Maybe, I don't know, maybe N, maybe R.
Maybe R. Okay. So there exists maybe a map which
Maybe P0. Let's say that this one is in A to the Z, and this one is in B to the Z. It's not exactly the same thing as I have written last time, because last time I wrote not a number, but I got influenced by you. I wrote like there is a finite shape, and you add I to the finite shape. But you know that all finite shapes can be embedded into a segment of the form minus n minus r. So this formula is equivalent. So, maybe we can show that Y is an SFT with order K plus R. Or K plus 2R maybe.
K to the order of original.
Yes. Order K means that we can take the finite pattern to be included in A to the K. So now I want to prove that Y is an SFT of this order. How do I do this?
I think we can assume that phi is like grouping, forget composition or grouping and trivial homomorphism.
I think that's very good, yes. Good. So you remember there is another characterization which is which is equivalent. But, so, yeah, I don't know. Actually, if I write it, it will be the same. But you see that you can group these 2r+1 letters, and then you have a map which is symbol-wise. Okay, so
And then you can construct a list of forbidden words for while. You need like forbidden words which defined by groupings. So now it can view like letters, like symbols of Y as groupings of 2r+1 elements of our alphabet A. So like, and then we can build a list of forbidden patterns for Y. And it will contain forbidden patterns which comes from the fact that we used grouping to construct the isomorphism. And a list of forbidden patterns which like which like
You try to get or construct the forbidden pattern. I don't know.
if you like concatenate them with join them, they will have forbidden patterns.
Yes, but actually, I think so this equivalence is not true as I wrote it, because it's equivalent to only these two lines. So we have to remember also to use, if I don't have reversible, I just, for example, it's just a factor, then this is not true. Y is not always an SFT. So we have to use the reversibility. What does the reversibility say? It's not only bijectivity, it's bijectivity, but also by the compactness. You know that the inverse is
It's actually important that we can define every pattern in Y by this map. Because if Y has maybe some extra patterns, it won't be true. Which are not like images of elementary X.
So, but formally, so, yes, so, okay, I finished. So, we can use the fact that there is another map. Maybe it's not the same R, but I take the maximal of the two R's. Or maybe I take an R prime, so that you understand better what's happening. And for all Y, phi minus 1 of Y, position I, is equal to psi 0 x I minus R prime, I plus R prime. I wrote that there is an inverse conjugate, an inverse homomorphism. So I think you have more or less all ideas. You want to try to write them on the board? And be helped by the other students.
I don't know if I can formalize it correctly, but
maybe you can. You have a list of forbidden patterns, and then you can take a configuration.
Say that our like morphism, our isomorphism P is something like tau additionally, like grouping maybe, like grouping like something like want to use the fact that y is equal to like image map phi, so every like pattern y is actually equal to phi of some x, and then I want to define like set forbidden like that we don't come up with set forbidden words, which like union of two sets. So we can use this trivial morphism tau on words, yes? Because it just changes letters to some other letters. It has words of okay, let's say it is image under tau minus 1, okay? So the groupings of form like
Maybe you can just say that the image is the language of order 2, maybe of order 2 plus k,
yes, just
of
all groupings.
groupings of
X, that's correct. Because actually I think if k is less than
yes.
than these two are plus 1, then we actually can have like just like a set of
Yes.
like simple words which has forbidden multi-sides. But if they are longer, then we need to put some like 5 words.
Okay, so maybe we can even suppose that 2r plus 1 is bigger than k, because if it's not the case, we can artificially increase r. You agree that this thing here is still true. If I take bigger r, then it's even more true, because I can take phi 0, which ignores some letters on the left and on the right.
Groupings. Let's just say like groupings x, because x is a word now in this language. In like in language like just a to z x such that maybe a is a subword of x and a is forbidden pattern in. How do you notice that? Right.
A is the word.
Subword,
So let's agree on this. So for me, using A denotes the symbol, and
no, it is
you don't use. I mean, I don't.
No, okay.
If you write it in the exam, it's not important, but
Just let's take maybe the first letter of
so actually, what we want to.
and now you probably need to check that this like actually defines our language like because we know that every word is in some word x, so each every part, every maybe configuration y is the image of the configuration, some configuration x under phi. So it must satisfy this constraint. This image under
Yes, but you're saying that every configuration must satisfy this.
contain.
And then we want also that every configuration which satisfies this is valid. So maybe just to summarize what you've done so far, I recall that the grouping operation decreases the order. So actually, we can group by r plus 1, by 2r plus 1, and we can group by the maximum of 2r plus 1 and k minus 1 maybe of x. And this is an SFT of order 2. You remember we saw this? Okay? So actually we can just assume that our phi is a symbol-wise map. Because the grouping, we know that it preserves, it decreases the order, but in particular it preserves finite type. Now we want to say that tau so maybe let's call this x tilde. We want to show that this is still an SFT if tau is a symbol-wise map, which is bijective, which means that we have phi 0 like this. And to prove this,
Do you want to meet for this?
Okay, no, I don't. No. So, but you didn't use the inverse, I think, yet.
No, we actually use inverse second at this moment to say that y is image. Y?
Yes, but no, you didn't use the inverse, the invertibility, because if you just use that it's surjective, this is false. You have surjective images of surjective. You have
because yes, we can prove that tau now is objective. So because if it wasn't objective, you would get some point where it would glue maybe two different configurations together.
Yes. So, but to prove that subshift is an SFT, what you want to do is to take the configuration which agrees for every position which agrees up to some length with a valid configuration, and then you show that this is a valid configuration. So, but okay, so this argument first simplifies a lot. So it remains to show if tau is symbol-wise. You remember what it means, symbol-wise? It means that I apply a map, an alphabet map to each letter. And there exists R prime in N and psi 0 and 2R prime plus 1 to A, such that for all I, all y I. Now I assume my phi is tau. Tau minus 1 of yi. equals y0 of x minus r prime plus r prime. And also I assume that x has order 2. So basically I replace my x tilde by x and my phi by tau because it's simple. Let y hat be the SFT on B defined by forbidden patterns. Maybe I want to say what's the English word? That coincides with tau of x forwards of length maybe 2r prime plus 1. So it's the SFT on B of order 2r prime plus 1. You understand what this means. So I fix a list of patterns of length 2r prime plus 1 that I accept, and I forbid the complement, and I accept exactly those that I can see in one image in tau of x. Okay? And this is a good candidate to be equal to y. By the way, this is y. So there is one inclusion which is obvious. Usually, so this is called the SFT approximation, which means when you have a subshift, you can approximate it by SFT with order bigger and bigger. And the SFT approximation is usually included, or it includes the subshift.
No, it's not the bigger one.
Yes. This is always true. You forbid exactly the forbidden words that don't appear in Y. Coincides. This means L2R plus 1 of Y equals L2R plus 1 of Y hat. Coincide means it's equal. It's equal for this, okay? It's not a mathematical term so much. So, but do you agree that this is a definition of a subshift of finite type? There is only one such subshift of finite type of order 2r plus 1, or phi plus 1. I take all the patterns that I see, and I forbid the other ones. But in Y, there could be longer patterns that are forbidden also. So Y is included. But all configurations of Y, they are patterns of length 2r prime plus 1, or in the allowed patterns of Y, so they are in the allowed patterns of Y hat. And since Y hat is an SFT of order 2r prime plus 1, then these configurations are in Y hat also. Now we want to prove the contrary. This is usually the way we prove that the subshift is of finite type. What you want to prove when it's a subshift of finite type of a given order is you take a sequence which is valid up to this order, and you want to show that actually it's really inner subshift. Do you see how we are going to do this? So, this is wrong. So I have this y, and I know that if I have a pattern, any pattern of length 12 prime plus 1, I know that it is in y. Maybe I should have one. Maybe it's 2r prime plus 2. So what can I do with this pattern? So I want, here I have y, and I want to prove, so I know that all of these windows, they are valid. And I want to prove that y is globally valid. Y is, capital Y is shift invariant, capital half Y is shift invariant. Shift invariant is implicit everywhere. It's not very, not a very big argument. So now, if I apply psi 0, I get a letter. Psi 0 is defined. Psi 0, actually in general, psi 0 is defined on L, the 2r prime plus 1 of y. It doesn't make a big difference. You can always extend it to the full set of words, but we don't use it. It's usually simpler to remember it like this. But what is interesting here is that psi 0, I can apply it in parallel to every pattern of y. Even if I don't know yet that y is in capital Y, so I don't know if I can apply I don't know if I can apply psi. Psi is the inverse of tau. Psi is the inverse of tau, and psi 0 is no, okay. I wrote it tau minus 1, sorry. So tau minus 1 is the map from y to x. Okay? And I don't know if I can apply tau minus 1 to this configuration, because I don't know if this configuration is in Y. But since I know that tau minus 1 comes from a local rule with this radius, and since I know that this configuration has valid patterns of this corresponding radius, I can apply psi 0, the local rule. I can apply it everywhere. And I obtain a configuration. Okay? And so how can I, maybe I can call this one psi of Y, configuration. This configuration is in D to the Z. No, is in A to the Z. So we don't know if it's in X. And now I change what I want to prove, and I add a 1. Sorry, because I always get it wrong in the first place. So what does it mean? It means that here I know that this big pattern of size 2r prime plus 2 is in my subshift, which means that if I apply the map here to get the second letter just next to it, I know that these two letters correspond to a valid pattern of length 2 in X, because there exists a valid configuration which extends this pattern of length 2 r prime plus 2 in Y, and when I apply the local rule of the inverse map of tau to this big configuration, I should get a valid configuration of X, and actually it turns out that I get exactly this pattern here. Do you want me to write formally what I've just said, or maybe? So, if for all I y I plus r prime minus r prime y plus r prime plus 1 is valid in Y, it means there exists Y, how can I call it? There exists Z in Y such that this pattern appears in a valid configuration of Y. Maybe Z index I put the index above, I told you I think once, because to not say that it's a letter. This is the definition of Y hat. By definition of Y hat, for all I there exists a valid Zi like this. But then, psi tau minus 1 of Zi in I plus 1 tau minus 1 of Zi is in X, because tau minus 1 is defined for every the map from Y to X, which is surjective and injective. So, A minus 1 of the I in I plus 1 is a valid pattern of length 2 in X, but this is equal to psi 0 of Y I minus R I plus R psi 0 of Y I minus R plus 1 I minus R plus R plus 1. So this is equal to psi of Y in I plus 1. What I have proved is that psi of Y for all psi of Y, all patterns of length 2 in psi of Y are valid in X. So what does it mean? You remember that X has order 2. So it means that psi of Y is in X. But then, if psi of Y is in X, what is equal to psi of Y? Then it should be equal to Y, because it's a symbol-wise map. So if I apply this, yes, I should find exactly the central cell here. I have a feeling you're not following completely, but it's much easier than you think. Maybe I didn't explain it the easiest way. But so when you want to prove that something is an SFT, you always do like this. You take a configuration which is locally valid up to some order, and then you prove that this is valid. And to prove that this is valid, you use all the assumptions. You use that there is an inverse map, you use that there is a... So I say that it's not true if you don't assume that there is an inverse map. First, is there any questions about this proof? Honestly, if you didn't follow completely, you can do it at home, quietly at the moment you have time, and you will see that it's not so hard if you just think about using all the assumptions. So, the counterexamples for when you don't assume that this is a conjugacy, when you just assume that it's a factor map, are linked to the questions we dealt with yesterday at the end of the course. So, you remember this thing with at most one and we agreed at the end that there was some kind of finite memory needed to check that the configuration was valid. And this finite memory can also be represented in some sense as a graph. For example, a loop. Someone said there is one bit memory, so one bit is two states. I can be either in state I have seen the one, or in the state I have not seen the one. So if I am in the state I have not seen the one, and I see only zeros, then I stay in the same state. Also, if I am in the state I have seen the one, okay? I don't change the state if I see only zeros, it's correct. And if I see a 1 being in state, then I change state. And if I see a 1 here, I can't. So I don't write anything. Do you agree that if I look at this path here, this represents exactly the subshift I said yesterday of the sequences that have at most 1, 1. The binary sequences that have at most 1, 1. Of course, it can have none because I can stay in this state forever. I have an infinite path. But we said yesterday that it's not an SFT. Did you finally prove it? Okay, this will be an SFT. So we said that graph.
Because we have like two loops with the same symbol.
Exactly. So it's not exactly the same definition of path. Here, I'm not dealing with the path itself. I'm dealing with the labels of the path. So here, there is a configuration with only zeros, which has two paths labeled by 0. Okay? So if I take this graph, I forget about the labels. The edge subshift is not exactly the same as the set of labels of this graph. There is a definition of label subshift. So, do you think the edge subshift is conjugate to the label subshift? here, for example?
No,
No.
because it's not a subshift of finite type. And if they will conjugate, then they will be a subshift.
Can factor it.
Yes.
Yes.
Yes, I repeat louder, if you want. So, we said yesterday that the label subshift is the set of labels of infinite paths. The label subshift of this is the set of configurations without most 1-1, and it's not a subshift of finite type. And we said last week that all edge subshifts are subshifts of finite type. So they are not conjugate because it would be a counterexample of this theorem. But what did you add?
You can factor, like, take H subshift and factor it to get the label subshift. Because it will just like send just like by trivial morphisms, every edge to its label.
Correct. So the label subshift is a factor of the edge subshift. Yeah. So I will send you by email some exercises about all of this, and next week we speak about something else. And I hope the exercise will also help you to understand this notion of label subshift. I think I can try to, because it's not so hard, just you have to understand that it's a bit different from the subshift of finite type. Any question on what we've done today, yesterday, last week?